Hi everyone, it's James again. We're doing homework 8, problem 3, and the setup is 3 currents, I1, I2, I3, all the same magnitude, 1.57 amps, and they are arranged as in the picture. This is a square, and you have the third current is over here at a distance equal to these distances here. And we want to find the magnetic fields at A, B, and C due to these 3 currents. We know they are long straight currents, and they are going out of the page in each case. We know the magnitude of the B field due to a long straight current. It's mu sub naught I over 2 pi r, where I is the current and r is the distance between the current and the point where you're finding the B field. So at A, the distance from I1 to this point is this length here. By Pythagoras, we can show that it's A root 2, because this is the hypotenuse, the sides are A and A, and so you get that the hypotenuse is equal to square root of A squared plus A squared, which is square root of 2A squared, which is A, take the square root of A squared, times square root of 2. And the same thing holds here, and here for later, and here. And so at A, I'm going to figure the magnitudes of the B fields first. At A, the B field due to current 1 is equal to mu sub naught times I1 over 2 pi R1, which is, if I call the common current just I, then it's mu sub naught times I, the same amount for all 3 currents, over 2 pi times this distance, which is A root 2. And because the current is the same for I2 and the distance is the same for I2, you get exactly the same for the B field due to current 2. B field due to the third current is B3 is mu sub naught I3 over 2 pi R3, which is mu sub naught I, because they all have the same magnitude I, over 2 pi times the distance from I3, which is A plus A plus A to this point, which is 3A. Now, the little bit more tedious part is adding the B fields as vectors. The B fields are vectors, so you have to add them as vectors. To do that, you need to figure the direction of the B field due to each current at the point A. So think about current 1. It's a long straight current, so the B field it generates is tangent to a circle centered at current 1. The Amperian loop for the long straight wire is a circle. That's the most convenient thing to use because the B field is tangent to the circle everywhere. And so if you think about a circle centered at current 1, goes around like this. So tangent to that circle is perpendicular to the radius of that circle. Well, the radius of that circle is this line here. So perpendicular to the radius is either down this way or up that way. To figure which of the two it is, we use right-hand rule 2. The straight bit is current 1, is the current. So I put my thumb in the direction of the straight bit, which is out of the page, so up. My fingers curl in the direction of the curly bit, so counterclockwise. Counterclockwise, if you think of a clock centered here with the face like that, the hands would be going counterclockwise, would be going this way. So that means that the B field is that way due to current 1. For current 2, here's current 2. The circle centered at current 2, because it's a long straight current, is like that. You use the circle because it's long straight current. B field is tangent to that circle, which means perpendicular to this radius, which means either that way or that way. Right-hand rule, current this way, fingers curl counterclockwise. Counterclockwise at this point relative to the center of the clock here goes like that. So it's that way. So that's the B field due to current 2. Same thing for current 3. The circle is like this, centered at I3. Tangent to the circle is either up or down. So right-hand rule, current 3 is out of the page. Fingers curl counterclockwise. So counterclockwise is down at this point. Okay. Now, we need to find the sum of these 3 vectors. So the x component of that sum is easy. I chose x to be to the right and y to be up. So the x component of B1 is minus the x component of B2, because B1 and B2 have the same magnitude and they're at the same angle with respect to the they're at the same angle with respect to the x direction, right? This angle is going to turn out to be 45 degrees, and this angle is also going to turn out to be 45 degrees because this is a right angle here. So the whole thing is 180, and this is 45 because you have a square. So 45 plus 90 is 135. Total is 180, so this is 45. So this angle here and this angle here are both 45 degrees. And so the x components of these two are equal and opposite. This has a positive x component, which is the magnitude B1 times cosine 45 degrees. This has a negative x component, which is magnitude B2 times cosine 45 degrees. But B1 equals B2, so the x components cancel. Plus, minus goes away. This one, B3, has no x component because it's straight down. So the total x component at A, at the first point, is 0. Just by symmetry. And the y component, remember, to find components of vectors, you first of all, it's plus or minus. So I'll write this out. B at A due to 1y plus B at A due to 2y plus B at A due to 3y. So B at A due to 1 in the y direction is it's going to be minus because it's pointing down. It's going to be the magnitude, which is B1, times sine of this angle, because here's the y direction and it's opposite the angle. And so the mnemonic is if the direction is opposite the angle, you use sine. And it's 45 degrees, so it's sine, B1, sine 45 degrees. And if you do the y component of B2, it's going to be the same thing because B2 is down, so it's minus. It's you multiply them by the magnitude, or you take the next part is the magnitude B2. Well, B2 is the same as B1, so minus B2 sine of 45 degrees again, because we talked about the fact that this is also 45 degrees. So you get the same thing for B2 in the y direction. So you can just multiply. I'll write it here. Minus B2 sine 45 degrees, which is just going to be the same as this. So you're going to get a factor of 2. And then B3 is going to be, well, B3 is down in the minus y direction, so minus the magnitude B3. And there's no cosine or sine because all of it's in the y direction. So it's just all down. So the y component of B3 is the minus the magnitude of B3. Okay, so this and this are the same because B1 and B2 are the same. So you get minus 2 times B1, which is mu sub naught I over 2 pi R1, which is 2 pi a root 2, times sine of 45 degrees, which is 1 over root 2. And then B3 is the mu sub naught I over 3 times 2 is 6 pi a. Then we get, let's see, let me bring out the mu sub naught I over 2a, because we're going to be getting factors of that for the rest of the problem. So mu sub naught I over 2a. And so, and a minus sign. So the 2's cancel here, and I get 1 over root 2 times 1 over root 2 is a half. Let's make sure I included everything. Mu sub naught I over pi a times a half, yep. And then this is mu sub naught I over pi a times a sixth, so 1/2 plus 1/6. And I'm going to calculate the mu sub naught I over 2a because we're going to keep getting it in the rest of the problem. So mu sub naught is 4 pi times 10 to the negative 7 Tesla meter per amp. I is given as 1.57 amps over 2 times A is 0.95 centimeters. We want MKS units, so 0.95 times 10 to the negative 2 meters. 1/2 plus 1/6, 3/6 plus 1/6, 4/6, or 2/3. So I'm going to calculate this just so I'll have that number for later. And I'll pause while I do that. Okay, so there's a professor who says that whenever you have a page of algebra, it has 3 errors. Well, I'm on my first error because this 2 was supposed to be a pi, right? There's pi here, pi there. That was supposed to be pi. So pi a, mu sub naught I over pi a. This is pi. And so if you calculate it, you get this number for mu sub naught I over pi a. 6.61 times 10 to the negative 5 Tesla times 2/3 comes out to be 4.41 times 10 to the negative 5 Tesla, or 44.1 times 10 to the negative 6 Tesla, or microtesla. So these are the components. 0 for the x component, 44.1 microtesla for the y component. And if you write that as magnitude and direction, then I'm sorry, forget my minus sign. Yeah. If you write that as magnitude and direction, then it's magnitude of a vector with a 0 for one component and a number for the other component is the absolute value of the number. And so the magnitude is 44.1 microtesla, and it's entirely in the y direction, or the minus y direction. So in the minus y direction, or down. Okay, that's the first part. Some of the work we've done will carry over to the other parts, so things will go a little faster from here on. So for B, the magnetic field at point B, I have magnetic field due to current 1. Again, is tangent to a circle centered at current 1 passing through B, because the circle is the convenient Amperian loop for long straight current. So tangent to this circle is perpendicular to this radius, so either right or left. Put my finger in the direction of current 1, fingers curl counterclockwise. And I'll stop doing this because it's always counterclockwise for these three currents coming out of the page. So it's counterclockwise. If I look at a clock like this, counterclockwise is going to be that way, yeah. Because this would be going backwards around the clock. Likewise, counterclockwise for a clock centered here, here's the circle, would be going left. And so B1 and B2 are going to cancel. That's convenient. And then for 3, again, here's the circle. It's counterclockwise by the right-hand rule. And so this circle, the tangent to it is either up or down. Counterclockwise is down because going around this way is counterclockwise. So here's B3. So again, we have that the x component of the B field at B is 0 because the x components, because these two B fields cancel, and B3 has no x component, it's straight down. So the B field at B, the x component is 0. The y component is, it's minus because, so the y component is just the same as B3 at B, its y component. So it's negative because B3 points down in the minus y direction. I chose y to be positive going up. So it's minus the magnitude B3 at the point B. Be careful because the magnitude will have changed. Times nothing because all of it is down in the minus y direction. So this is equal to minus, remember the magnitude of the B field due to a long straight current is mu sub naught I over 2 pi r. So in this case it's I3 and R3. And so we get minus mu sub naught. I3 is just that value I over 2 pi times R3. Well, R3 is the distance from the current to the point B where we're finding the B field. That is A plus A, that's 2A. All right. And so I calculated mu sub naught I over pi A, so I'll bring that out. And I've got a 1/4. And notice it's going to be smaller than the B field over here, even though it's closer to the currents because the B fields due to 1 and 2 canceled. So that mu sub naught I over pi A, that was the minus 66.1 microtesla times 1/4. So that comes out to be 66.1 divided by 4 is 16.5, and it's minus 16.5 microtesla. And again, the B field at B is all in the y direction, the minus y direction. So the magnitude, there's no x component, so the magnitude is just the magnitude of the y component. So the B field at B is 16.5 microtesla in the minus y direction or down. And then C, point C is over here. And again, we've got circle centered at current 1 has this radius. So the B field's tangent to the circle, perpendicular to the radius, so it's either that way or that way. Counterclockwise is going to be that way because you're going around like that, right? So that's B1. B due to 2 or B2 is perpendicular to this radius because here's the circle it's tangent to. So it's either that way or that way. Counterclockwise is going to be that way because you go around like this. So B2 and B3 is tangent to this circle. So it's either up or down. Counterclockwise is down because at this point, relative to that current, because you'd be going around this way. So that's that. So B3, sorry, the diagram is so busy. If I look at B1 and B2, again, the x components are going to cancel. They're equal magnitude pointing in opposite directions in x. So again, B, now it's B at C we're up to. So B at C, x component is 0. And the y component, now I'm going to go back to the work I did before because the y component at C, notice, compare this to this. For 1 and 2, it's the same as here, except they're pointing up instead of down. Notice that the distances are the same, a root 2 always. So for 1 and 2, it's the same as here, except the y component is up instead of down. And so remember the y component from the first part was minus mu sub naught over pi a times a half for the total of 1 and 2. So I'm going to take that and you think this through. Verify it for yourself. In fact, the best way to use these videos is to watch them as the parts that you need after you've tried the problem. And then stop the video and continue the problem. And later come back and try the problem without watching the video. Anyway, so the y component is going to, for the sum of the y components for 1 and 2. Yeah, we've got the sum of all the y components. The sum of the y components for 1 and 2 is just going to be, instead of minus mu sub naught I over pi a times a half, it's going to be plus mu sub naught I over pi a times a half. Because if you look here, 1 and 2 gave these two terms, which gave this, which gave this times that. So instead of minus, it's just plus. So I got plus, yes. So plus mu sub naught I over pi a times a half. And for B3, now the magnitude of B3 is different because now it's closer. But it is again all down. There is no x component. So the y component is just the magnitude of B3. It's B3. So the y component here is just minus B3 at the point C. And I'm going to have to figure that out. Bad notation. Okay, so this is what I mean. Right? Because this whole thing is the sum of the y components for 1 and 2. And then B3C, I'm just taking off by itself. And I'm going to work on what that is now. So I've got mu sub naught I over pi a times a half minus, remember, the current 3 is a long straight wire, so you use the expression mu sub naught I3 over 2 pi R3. And so I3 is just I. And R3 is just A. Because if I bring this back one last time, the distance from I3 to point C is just A. So it's over 2 pi R3, so over 2 pi A. Good. And then I can bring out the mu sub naught I over pi A, and I get 1/2 minus 1/2, and I get 0. So the magnitude of B at C is 0. The direction of 0 is, it has any direction. It has no direction. It's so BC is just 0. Okay, and I got 0 here. The reason is the y components here have a factor of 1 over root 2 due to the sine, and 1 over root 2 due to the, let me be careful. Yes, 1 over root 2 due to this, the trig function, and 1 over root 2 due to the 1 over r in mu sub naught over 2 pi r. So each of these two has a factor of 1/2, and there are 2 of them, so you get 2 times 1/2 is 1. 1 times mu sub naught I over pi a. And then this one is just a minus mu sub naught I over pi a. Yeah. And then there's the factor of 1/2 from the 2 pi r. I was ignoring. All right. So that was a long problem. Hopefully that was helpful, and hope you have a good day.